Hey everyone, and welcome to The Explainer. Today we're diving into a really fascinating chapter called A Peek Beyond the Point. I'm honestly so excited to guide you through this one, mostly because we're going to look at something we literally encounter every single day, but probably never think twice about. We are going on a journey exploring the hidden power of decimals. We'll be starting really small with the kind of tiny everyday measurements you might make at your kitchen table and scaling all the way up to see the massive real-world consequences that happen when we get those tiny fractions wrong. So let's get right into it.
So picture this. There's a highly relatable story right at the start of the chapter about a young boy named Sanu. He's watching his mom try to fix a broken toy, and she's trying to join two pieces together with a screw, but it's just not catching. It isn't working. When Sanu asks why, his mom explains that the screw simply isn't the right size. She pulls another one out of the box, tries again, and boom, perfectly fixes the toy. Now, to Sonu, those two screws looked exactly the same, but when he looked closer, he realized one was just slightly too short.
And, that observation brings up our central question for this explainer. Why does a fraction of a centimeter even matter? It perfectly frames exactly what we're looking at today. How can tiny, almost invisible differences in length completely change an outcome? A toy either holds together or it falls apart, all based on a measurement so incredibly small it's hard to even see. So what tool do we actually use to see the invisible?
All right, Section 1, Decoding the Ruler. To really understand how we measure these tiny differences, we have to look at how a standard ruler works. As the chapter breaks down, to get more accurate than a whole unit, say a single centimeter, we have to split that unit up into smaller, equal pieces. First, we slice a unit into 10 equal parts, right? We call those tenths. And if we need to be even more precise than that, we split each of those tenths into 10 more pieces, which gives us hundredths. This whole process of division is the absolute foundation of precise measurement.
And the text uses a brilliant example of 3 screws to show why this division is absolutely crucial. Just like the screws Sonu was looking at, they might seem identical at a quick glance, but when you measure them against a standard ruler divided into tenths, the differences are instantly clear. Take the longest screw, for example. You start at 0, go past the 2 centimeter mark, and then you count 7 tiny lines. That means the screw is exactly 2 whole centimeters and 7/10 of a centimeter long. Without those tiny fractional markings, we'd literally just be guessing. But honestly, writing out all those fractions all the time, that can get super complicated.
Moving right along to Section 2, Fractions to Decimals.
Okay, so writing out fractions like 7/10 every single time we measure something gets old fast. It's messy, so we use the decimal place value system instead. You're probably already familiar with hundreds, tens, and units, but the real magic happens when we jump past that unit value. We just drop in a decimal point, and suddenly we have this incredibly clean, organized way to write our tenths and hundredths. We can completely skip writing out those messy fractions. It's a real game changer.
Let's actually break down the math using an example straight from the chapter, just to see how elegantly this system works. Say you have a measurement of 244 tenths. We can easily break that down into 200 tenths plus 30 tenths plus 4 tenths. Or, if we simplify it, that's 20 plus 3 plus 4 tenths. By using our decimal place value system, all of those fractions perfectly collapse into one clean number, 23.4. It is the exact same value, just written in a way that is incredibly fast to read and calculate.
Which brings us to Section 3, Measuring the World.
You see, decimals help us measure absolutely everything in our physical environment. They bridge the gap between man-made objects and the natural world. The chapter shows us everyday items, like an eraser and a pencil, easily measured out, the pencil ending precisely at 4 5/10 centimeters, or 4.5. But then, we see the exact same mathematical system applied to the intricate anatomy of a honeybee. It allows us to quantify the complex proportions of nature with total ease.
In fact, the chapter walks us through this amazing little exercise where we add up the decimal components of that honeybee to find its total length. The head is 2 3/10 units long, the thorax is 5 4/10, the abdomen is 7 5/10. If we add those all together, just combining the whole numbers and then the fractions, we get exactly 15 2/10 units, or 15.2. It just proves that whether you're building a desk or studying an insect, the math works seamlessly. But what happens when humans mess the math up?
Now for the crazy stuff. Section 4, Real-World Decimal Disasters. Well, a decimal point is physically tiny. Misplacing one can have catastrophic consequences. Imagine this massive number, 188 million euros. Back in 2013, the finance office of the Amsterdam City Council accidentally sent this staggering amount of money out to citizens for housing benefits.
Seriously, just let that sink in for a second. 188 million euros.
The wildest part? The intended amount for those benefits was only supposed to be 1.8 million euros. So, how on earth did this incredible financial disaster actually happen? Well, as the text points out, it was just a programming error. The software processed the payments in euro cents instead of whole euros. Remember earlier when we talked about slicing a unit into 100 pieces? The computer completely confused a whole unit, the euro, with the hundreds, the cent. That one simple failure to respect the decimal point inflated the payouts by 100 times.
But honestly, the stakes can get way, way higher than just money. The chapter highlights this horrifying unit mix-up from 1983 involving Air Canada Flight 143, a massive Boeing 767. The ground staff miscalculated the aircraft's fuel. They loaded 22,300 pounds of fuel. But the plane's computer, it required 22,300 kilograms. The staff completely failed to account for the conversion decimal. Since 1 pound is roughly 0.453 kilograms, ignoring that tiny decimal meant they only loaded about half the fuel the jet actually needed to make the trip.
And the result of that missing decimal was a terrifying mid-air crisis. The plane literally ran out of fuel while cruising at high altitude. The engines just stopped. The pilots were forced to turn this giant commercial jet into a glider, executing a crazy emergency landing in an abandoned airfield. Miraculously, everyone survived. But it is a chilling reminder of how a single decimal conversion error nearly cost hundreds of lives.
And that brings us to the end of our explainer today. We started with a young kid just looking at a screw, and we ended with a falling airplane, all connected by the simple math of fractions and decimals. So I want to leave you with this to chew on. If a single decimal point is powerful enough to empty a major city's bank account or ground a commercial jet in midair, are you paying enough attention to the space beyond the point? Definitely something to think about the next time you measure something. Thanks for learning with me today.